Hello, and welcome to this introductory lecture on fluid flow and pressure losses in pipes. My name is Matt. I'm an assistant professor here in the School of Chemical Engineering at the University of Birmingham. This lecture is designed to give you an introduction to what a university-style lecture looks like, and the sort of material we'll be covering is typical of a first-year undergraduate degree course. There will be some maths involved, but that shouldn't be too much above GCSE or A-level standard. So, as I said, this is what we're going to be talking about. This is the point of this lecture. And as well as introducing a university-style lecture, I'll be putting some physical laws into context. So especially if you're studying a physics A-level, you might have heard of some of the concepts that I'll be talking about over the next 40-45 minutes or so. And then, also as I mentioned, we'll be bringing some maths into it. But this won't be your sort of pure maths that you learn at GCSE and A-level. It'll be a bit more applied to a real-life engineering context. So, as part of that, we have 4 key learning objectives here. The first is going to be understanding how we use pipe flow in real-world applications. We're going to develop an understanding of how fluids, and that means gases and liquids, how they move in pipes. We're going to be looking at their flow regime and velocity profile, and I'll explain a little bit more about what that means later on. Thirdly, we're going to be understanding why there are some pressure losses in pipes, and then finally, we'll develop a mathematical expression for calculating that pressure loss. So first up is understanding the application of pipe flow in a real-world setting. So if you're watching this back at home, take a few minutes just to name any household items where fluid flowing through a pipe is important. I say a few minutes, actually I mean more like 20 seconds. Have a little think about what your typical household might have in it, where fluids might be flowing around it, and maybe just jot down a few example ideas. If you'd like to at this moment, you can also pause the video just to give yourself a bit more time. Okay, I had a think about it, and the first thing I thought of was a radiator. Most households will have some kind of central heating system where hot water is heated and it's transported around a house. So of course we need to understand how that hot water is flowing through all the pipes in our houses. If you think about a car, it's a bit more of a complex system than a radiator in some ways, but in those cars there is an engine, and in an engine you'll have fluids moving like coolants and oils. If you think about on top of buildings, there's probably going to be some kind of air conditioning system. So on the screen here is an example of that air conditioning unit on top of a building. Showers. I like a nice powerful shower, so you want to make sure there's a good hefty amount of pressure coming out of the shower head after it's been pumped through all of the pipes in our houses. And then finally, something like a fridge. If you flip a fridge over, you can see it has a bit of a radiator at the back. There is a compressor at the bottom which compresses our coolant, and then there's also coolant tubes where the coolant flows around the back of our fridge to remove the heat out of it and keep it nice and cool. When it comes to more chemical engineering applications, and we think of a chemical plant, well, here, fluids moving is also very important. We might want to supply cooling water or heating water to various different parts of our system. If we're thinking about a boiler, we also need to be supplying some natural gas. When we have our reactor, well, we need to move our reactants into the reactor, and then we need to remove our products out of it as well. It's quite rare that we generate a pure product straight away, so we might also need to separate them out and purify them. And then once we have our pure product, we need to be able to pump it into some kind of storage facility. And all of this will involve moving fluids around. I did mention earlier heating and cooling. Quite often we're having to heat things up or cool things down using pieces of equipment such as heat exchangers, and all of these will involve moving fluids. And finally, one of the key parts of chemical engineering is carrying out chemical reactions. And if we are thinking about something like a plug flow reactor, here we have reactants flowing together along what is essentially a pipe and reacting together. So all of these different things come together, which means we need a very thorough understanding of what how do we actually do it? Well, we could do it under gravity. So we think about some houses, they will have a storage tank at the very top, and we just let the water flow down our building into our various different applications. But one of the main ways is by using some kind of pump. There are two main types of pump that we like to consider. The first is centrifugal, and this will typically be used for moving low viscosity fluids, things like water, organic solvents like methanol or ethanol, or sometimes acids as well. Centrifugal pumps look a little bit like this, and you can see how there's almost two sections to this pump. There's a head part where our blade sits, and then a motor towards the back. Front face here is where our fluid goes in, and the outlet is situated at the top. We also have what's called a positive displacement pump. These are used for moving higher viscosity fluids, such as oils and paint, around different chemical factories, and they look a little bit different. They look a bit like this. They generally consist of some kind of piston, which is also located at the front, and this piston will just move up and down, alternately drawing fluid in and expelling it out through a different part of the network. Okay, so that was some applications of pipe flow in the real world. Now we're going to take a look at how they flow in pipes, focusing first off on their flow regime. So when fluids move, there are normally three states in which they can be in. The first is laminar flow. Laminar flow is where those fluids are moving in very parallel streamlines, and they have very distinct layers. So there's no movement in between those layers, there's very little mixing, and they generally occur under a low flow rate with a small pipe diameter and with very light or very viscous fluids. You might be able to see on the screen at the moment, there's an animation playing where we've got a straight streamline of a single fluid moving in laminar flow. They could also be turbulent. Now in turbulent flow, there are random eddies of the fluid across the pipe diameter. So we can see in the animation here that we inject a little bit of dye, and very quickly, in a very short length of pipe, that dye becomes fully dispersed across the diameter. And that shows there's a lot of mixing going on, and that is characteristic when we have a high flow rate, a large pipe diameter, a very dense fluid, or a fluid with a low viscosity. So, does it matter whether we've got a laminar flow or a turbulent flow? And I'm pretty sure you can guess the answer is yes, it of course matters. In laminar flow, we have poor mixing, which means we might have a very non-uniform product. And we generally don't want to have a non-uniform product, but like everything to be consistent, because that means our products are going to be very consistent as well. It also means if we have what's called multi-phase flow, so for example, solids being transported in a liquid, those solids might settle out in laminar flow. And again, that's not good either, because it means we might have blocked pipes, and again, a very non-uniform product. However, under laminar flow, things like the pressure loss and the amount of heat being transferred in the pipe are a bit easier to predict. Also, if we have quite a delicate product, something like complicated proteins, we have to handle them quite carefully. They're very delicate molecules, so if we're pumping them along a pipe too quickly, those molecules could break apart. So we do need to be careful, and maybe we do sometimes want laminar flow. Turbulent flow is the exact opposite, as you might expect. Here we have a well-mixed system, and therefore a uniform product, but we have higher pressure losses in our pipe. And generally, we want to try and minimize those pressure losses, because a lower pressure loss will lead to lower operating costs and a higher efficiency. Okay. Unfortunately, most pipes are not like the clear, translucent tubes that you saw in the animations. They're often made out of steel. And of course, we can't see through that steel. So then how do we start to work out whether the flow is laminar, turbulent, or maybe somewhere in between? Well, over 100 years ago, someone called Osborne Reynolds did a set of experiments where he analysed how fluids move in pipes and at what point they start to become turbulent. As we can see here, we characterize turbulent flow by the formation of these random eddies across the pipe diameter. So, Osborne-Reynolds, he determined that the turbulence depends on four main factors: the velocity of the fluid flowing in the pipe, which we normally denote as a U, the diameter of the pipe, d, the density of our fluid, which is given by this Greek symbol we call rho, and also the fluid viscosity, which is given by another Greek symbol called mu. And he worked out that a certain ratio of what we call the viscous forces to the inertial forces will give us a certain number. And this number is now called the Reynolds number. It has no units, and that means it is a dimensionless number. There's an equation for it on the screen here, so we can see that if we multiply the density by the velocity and by the pipe diameter, then divide all that by the viscosity, we will get some kind of number which we call the Reynolds number. As you can see on the screen here, just highlighted that, we have the inertial force on the top, and that's the resistance to a change in velocity divided by the viscous forces, which is also described as the resistance to flow. And we can show that this is a dimensionless number just by writing everything out in our standard, what we call SI units. So we take our density, which is kilograms per meters cubed, multiply that by our speed or velocity, which is in meters per second, and then multiply that by our pipe diameter in meters, and then we divide that by our viscosity in Pascal seconds. But we know that Pascal seconds is equivalent to kilograms per meter per second squared. We write that out properly so we can see which units start to cancel with each other, and then we note that we end up with kilograms per meter times by per second divided by kilograms per meter times by per second, which means that they all cancel out, and we show that Reynolds is indeed dimensionless. For flow in a nice cylindrical pipe, Osborne-Reynolds showed that flow was considered laminar when this Reynolds number was less than 2,000, and it was turbulent for when Reynolds was above 4,000. When it's in between, this is what we call transitional flow. And generally, as engineers, we try and design our system to be outside of this transitional region, because things become very difficult to predict, they become difficult to model, and therefore it becomes quite difficult to simulate it as well. Okay, that's a lot of information all at once, looking at how we characterize the flow within our system. So let's take a look at some kind of example. Let's imagine we have our chemical, in this case octanol, flowing through a pipe of a certain radius inside a building. We have a given flow rate of 12 kilograms per minute, and when it leaves the building, a cold wind blows over the pipe, which means it rapidly cools down to 20 degrees C. That cooling causes a change in viscosity, so we want to know whether the flow regime, whether it's laminar or turbulent, will also change. Based on the information that's there, let's also have a think about what we need to assume about the fluid properties and whether that actually matters. So, as with any engineering problem, we start off just by writing out our key information. We take a look at what we've been given. So we know the density of our fluid, we know the radius of our pipe, r, we know our mass flow rate, which is denoted by m dot, and we also know the viscosity of our fluid at two different temperatures. We also have our equation for Reynolds number, which we use to characterize whether a flow is laminar or turbulent. We have our density in kilograms per meters cubed, so that's good. We have our viscosity in Pascal seconds, so that's good as well. We find diameter. Well, we have the radius, and we know that radius is half the diameter. So that means all we have to do is multiply our radius by 2, and we get the diameter of 0.15 meters. So, to find the fluid velocity, that needs a little bit more maths, a little bit more calculating. We have the mass flow rate, and we have the density, and we have the area of the pipe. So from these three things, we can then work out our fluid velocity. Convert our mass flow to a volumetric flow. Now we think about the units here, we've got mass flow in kilograms per second. The density is kilograms per meters cubed. So if we divide the mass flow by the density, it means we divide kilograms per second by kilograms per meters cubed. The kilograms will cancel out, and that means we're left with meters cubed per second. And of course, meters cubed per second is a volumetric flow. So I've done that calculation on the screen here, and we can see that we have a volumetric flow of 2.43 times 10 to the minus 4 meters cubed per second. And just showing that those units work, we can see that the kilograms cancel out there. To convert our volumetric flow to the velocity of a fluid, this is the average velocity that we've got across the pipe, because we don't know anything about the velocity profile at this moment in time. So all we do is divide the volumetric flow by our cross-sectional area to get the velocity. Then because we know our pipe is cylindrical, all we have to do is find the area of the pipe from using the equation for an area of a circle, which is pi r squared, or as I've written it here, it's pi diameter squared divided by 4. So that means we can calculate our fluid velocity as 0.0138 meters per second. And again, just showing those units there, we cancel meters cubed with meters squared to get meters per second. So, we have everything we need now. At 50 degrees C, we just substitute in our values for density, velocity, diameter and viscosity, and we get a Reynolds number of just over 4,000. So we know that initially, when the fluid is at 50 degrees, we've got turbulent flow. At 20 degrees, when our viscosity has dropped, our Reynolds number is much lower. It's only 224. So that means we now have a laminar flow. So yes, our flow regimes have changed. That means that how our fluid is moving in the pipe has changed, and therefore any pressure losses in the pipe are also likely to be different as well. So as an engineer, this is something that we need to be aware of. The second part of this question was to think about some key assumptions that we've made during this calculation. And that key assumption is, well, we're assuming that the density at 50 degrees is the same as at 20 degrees. But of course, as we heat things up, the molecules move further apart, and that means things tend to get less dense. So in reality, the density will decrease when the temperature goes up. But mass is conserved. We haven't lost any mass of our octanol. So we know that the mass flow rate at 50 degrees is equal to the mass flow rate at 20 degrees. Our mass flow rate is equal to our volumetric flow rate multiplied by our density. So we can say that the density at 50 degrees, rho 50, multiplied by the volumetric flow at 50 degrees is equal to rho 20 times by q 20. An expression for volumetric flow is to take the area of our pipe, A, and multiply it by our fluid velocity, u. So, if we write that out, we end up with rho 50 u50a is equal to rho 20 u20a. We note that the area of our pipe, is constant, so those two values will cancel out, and that means we have rho 50 u50 is equal to rho 20 u20. And that means we have shown here that any increase in density will be compensated for by a decrease in velocity. So in this particular situation, our assumption that the density is constant is probably okay, because any changes is balanced out by the velocity of the fluid. So, moving on from that example, we can now look at another of our learning objectives, which is developing an understanding of the velocity profile of our fluid. So what's that velocity profile look like? What do we mean by a velocity profile? Well, unfortunately, even in laminar flow, the fluid velocity is not the same across the whole diameter of the pipe. If we consider a pipe like this with a direction of flow moving from left to right, and we also have to consider the radial position of where we are in that pipe. So what we say is, we're at the centre, our radial position is 0, and at the edge of the pipe, our radial position is equal to, in this case, a capital R. at that pipe wall, at R equals R, the friction at the pipe wall, there is friction at the pipe wall, and that friction is so great that there's a small layer of molecules that don't actually move, and that's known as the no-slip condition. So because there's no molecules moving there, our fluid velocity, or U, will be equal to 0. That fluid velocity will gradually increase as we move from the edge of the pipe into the centre until we reach a maximum velocity, which we call U max. So that means we can write in two different conditions here. So we say at R equals 0, U is equal to U max, and at R equals capital R, we have U equals 0. And we start to use what we call these boundary conditions to help develop some equations a little bit later on. Now, the shape of this velocity profile will also depend on the flow regime, the fluid properties, and the roughness of our pipe. The shape of the velocity profile shown here is for a smooth pipe in laminar flow. And we can see we've got quite a steep, what we call parabolic profile. In turbulent flow, we have a much flatter profile. For a smooth pipe, there's much more fluid at the maximum fluid velocity, or U max, and you can see that we now have a much flatter shape to that velocity profile. As we increase the roughness of our pipe, the flatness of that profile will decrease, and we end up with more of a parabolic shape again, because there's more friction at the pipe surface, there's a thicker layer of molecules that have 0 or low velocity, and that means we end up with a more shallow curve and a greater velocity gradient. So that was a little bit about the velocity profile of our fluids. Now let's take a look at understanding why there are pressure losses in our pipes. Well, the primary reason is friction. And if we look at the pressure drop between, when we say pressure drop, what we mean is the difference in pressure between two different points in a fluid carrying network. So if we take our section of pipe, we have 2 points on it, P1 and P2, and the difference between those 2 points will be known as delta P, or difference in pressure. And because of those frictional losses, we know that P2 will be less than P1. And as I mentioned, the reason why there is that difference in pressure is all down to friction. We have what's called major losses, which are between the fluid and the pipe wall, and we also have minor losses, which is due to friction within the fluid itself. The magnitude of that pressure drop is dependent on what we call the resistance to flow. And that is a function of the fluid itself and what we call the system properties. The system properties are things like the flow regime, and it is also dependent on the roughness of the pipe. Because of course, if we have a rougher pipe, a rougher surface, we're going to have more friction. And the higher friction will lead to a higher pressure loss. The other thing to bear in mind is that this pressure loss is proportional to our shear force. Now, what we mean by a shear force is the forces are acting parallel to each other. So if you imagine pushing a door open, that's what we call a normal force, because the action of force is acting perpendicular to the direction of movement. In shear losses, those two things are acting parallel to each other. So if you rub your hands together, you can feel them heat up, and that's due to some shear forces being applied between the surfaces of your hands. So that pressure drop in our pipes will increase if there's a high shear force, if there's lots of fittings, so we have lots of valves or bends in our system, our pressure losses are going to go up. And it will also result in a higher pressure loss if we do things like go around a coil as well. Generally, we want to minimise our pressure losses. If we have a lower pressure loss, we end up reducing our energy costs, which gives us greater efficiency and enables us to save money. And that's another key aspect of being a chemical engineer, is looking at how we can improve processes and lower our environmental impact and lower our operating costs. So if we look now at our full system design, let's take a fairly simple system where we are just moving hot water from a tank through some pipes, and then upwards to a shower head. We need to provide enough energy to overcome our pressure losses, or delta P. There will be a frictional loss due to our straight or curved pipes, bends and any associated fittings. There will be some pressure losses due to pumping upwards and the fact that we need to overcome gravity. And then we also need to provide enough pressure at the outlet of our shower head so the water doesn't just dribble out at the end. Before we start looking at things like curved pipes and fittings and pumping against gravity, let's just look at predicting our pressure loss, our delta P, for a straight pipe. And that brings us on to our final learning objective for today, which is developing a mathematical expression for calculating pressure losses. So, before we start looking at that, let's have a look at differential equations. If you're just doing GCSE maths at the moment, don't worry too much about this, as you'll start learning about that over the next year or two. So essentially, differential equations describe how one variable changes when we change something else, or with respect to another variable. For example, if we take the equation for a straight line, y equals mx plus c, and we differentiate that with respect to x, we get dy by dx is equal to m. If we look at a cubic equation, for example this one here, and differentiate that, the derivative, or differential, is also shown here. And in terms of the rules around differentiating, you'll learn more about that, possibly at GCSE, but definitely at A-level maths, and we will recap that at university as well. But what these differential equations do is they show how y changes when we change x. And that can be expressed as the gradient of a line. There's two ways of thinking about it. Either we have an equation for y, and then dy by dx gives us an equation for the gradient of the line, or the other way of thinking about it is we have an equation for y, and dy by dx tells us how fast y changes when we change x. If we move away from these fairly pure maths equations, where we just look at two variables y and x, we can develop some physical or chemical laws. For example, if we have dv by dt, where v is velocity and t is time, how velocity changes with respect to time gives us our acceleration. If we look at chemical kinetics, we have our rate of reaction, Ra, is equal to our difference in concentration divided by difference in time, or dCA by dt. And that can be expressed as equal to our constant of proportionality, K, times by the concentration of our reactant, raised to the power of n. For a fluid flowing in a pipe, however, we don't necessarily need to look at accelerations or velocities or chemical rates. We instead look at a force balance. So we know from Newton's laws and the conservation of energy that all forces in a system must balance. So again, if we take our pipe and we have a direction of flow from left to right, and then we take a small slice of that pipe, which we call dl. Another way of thinking about this is our differential length. We have an amount of force going into that differential length. That force is contained within the fluid, and it's the force of the fluid pushing along the length of the pipe. And we can see here we have a force denoted by capital F plus a little bit more force, and we call that little bit more force dF. Now, because of some frictional losses, the fluid loses that little bit of force dF as it goes through our differential length dl. And those frictional losses can be denoted by this symbol here. We call this symbol tau, and that's due to the shear stress acting on the fluid, both at the wall and also within the fluid, as those molecules rub against each other. And the other thing to consider is that the force of that fluid goes into our cross-sectional area, and that cross-sectional area is denoted as dAc, and that's the area of the circumference around the pipe, not the cross-section of the pipe that the fluid flows through. So if we look at our force balance, we know that all forces must balance, so we can say the force going into our cross-sectional area is equal to our force coming out plus any losses. So, force in equals force out plus losses. Our force in is F plus dF. Our force coming out is just F. And our losses is this tau W. And that acts over our differential area, which we call dAc. So we can write that up mathematically as F plus dF equals F plus tau W times by dAc. And if you're studying physics, you might know that force is equal to pressure times by the area. So we can substitute that in for F, which gives us P times by AX, where AX is our cross-sectional area, plus dP AX, and that's going to be equal to PAX plus tau W dAc. We notice that our cross-sectional area will cancel on both sides, and that leaves us with dPAX equals tau W dAc. And we notice here that we've got two different areas. We have AX, which is the cross-sectional area, and AC, which is the circumference, the area of the circumference of the pipe. And now we can start substituting in using our well-known equations for circles. So we take AX equals pi r squared, or another way of writing this is pi d squared divided by 4. And we also take our circumference, the area of our circumference, which ends up being pi d L. We substitute in those values, and then we notice we can also start cancelling things out. Our pi's will cancel on both sides, our d squared will cancel with d, and then we can have what we call a differential equation. So what we need to do is we need to integrate both sides of this equation between our 2 points, our P1 and P2, which is our pressure loss between points L2 and L1. And that means we end up with an expression for P2 minus P1, or delta P. So we have delta P is equal to 4 times by tau W times by L divided by pipe diameter. Now we need to know an expression for those frictional losses tau W. And we know from various literature values that tau W is equal to our friction factor, or phi, which is that symbol with a circle and a line through it, multiplied by density multiplied by the square of the velocity. So that means we have a final expression for delta P, as shown on the screen here. And the only thing that we don't necessarily know very easily in this expression is our friction factor phi. And we find phi using a diagram called a Moody chart. This is a fairly simple way of doing it. When we're doing some design work, we might use certain engineering software, and that will often have friction factor values built in. The Moody chart, however, looks like this. It looks a bit complicated, but if we start breaking it down, we can see how it starts to make sense. What it shows is friction factor on the left-hand side, and that's the first thing that that's the final thing that we're trying to find. It plots that friction factor against the Reynolds number, which we know how to calculate from earlier, but we've also got a series of lines on there for various different pipe roughnesses. And that pipe relative roughness is calculated by taking our equation at the top right there. You take epsilon, which is the absolute height of roughness in that pipe, and divided by the pipe diameter. That absolute pipe roughness can be taken by looking at the average height of the surface defects within the pipe wall. So, to use the Moody chart, we first calculate our Reynolds number. We then calculate our relative roughness. We then identify the correct line on the right-hand side, which corresponds to that relative roughness. And then we follow that line along the curve, because they do curve towards lower Reynolds numbers, until it reaches the point that intersects with the Reynolds number that we've calculated. And then we read off the friction factor phi on the left-hand y-axis. That's a little bit difficult to follow, just with me describing it. So let's look at a real-life example of that. If we take cooling water from a storage tank and pump it to the top of a reactor, calculate the pressure loss per unit length if the water is transferred along a straight, horizontal stainless steel pipe with a given internal diameter at a given flow rate of 50 litres per minute. We also have the density and the viscosity of the water given there as well. So, same as before, we identify our key information. We have our density, we have the diameter of the pipe of 26.6 millimetres, volumetric flow rate, which I've also converted to meters cubed per second there, and we also have our dynamic viscosity in Pascal seconds. First up, same as before, calculate the velocity, take our volumetric flow rate, divide by our cross-sectional area, and that gives us 1.5 meters per second. As we now have our velocity, density, viscosity, and pipe diameter, we can calculate Reynolds number fairly simply, and we see we have a much larger Reynolds number than earlier. Here, it's nearly 40,000. So, now we go to our Moody chart. We identify the point on the Moody chart, which relates to a Reynolds number of 40,000. Calculate the relative roughness. So, because we know it's a stainless steel pipe, it might be a little bit unclear on the screen, but in the box on the bottom left-hand side, we have a number of different materials and their corresponding absolute roughness. For stainless steel, this is 0.025. We divide it by the pipe diameter to get our relative roughness of 9 times 10 to the minus 4. This is about 1 times 10 to the minus 3, or 0.001. So, we go to the line that's 0.001, follow it along the curve until it reaches our value of Reynolds number of 40,000. And you can see I've put a dot on the screen there. We then read our friction factor off the left-hand side, and we see that this corresponds to a value of 0.025. A couple of things to notice here. The Reynolds number at the bottom is in a scale which we call a logarithmic scale, which means it moves up in increments to the power of 10, rather than just going up in 1, 2, 3, 4, 5. And then the friction factor on the left is also on a logarithmic scale as well. So we have our friction factor, we have the equation that we derived earlier, but you notice that we've moved the length term, our L, from the right-hand side to the left-hand side, and that enables us to calculate our pressure loss, or delta P, per unit length, rather than being given a total length of pipe. So, now we just substitute in our values. We take our friction factor, which we've worked out to be 0.025, multiply by the density, multiply by the velocity squared, and then divide by the pipe diameter to get a value of around 8,500 pascals per metre, because we were asked to work out the pressure losses per unit length. And that brings us towards the end of this example lecture. We've looked at the application of pipe flow in some real-world settings. We've also developed an understanding of how gases, liquids, so all fluids, will flow in pipes by looking at what a flow regime is and what a velocity profile is. We've also talked about why we get these pressure losses in pipes, and then finally we've developed a mathematical expression for how we can calculate those pressure losses. Thank you very much for watching this, and if you have any questions or would like to catch up on anything, do use my email address at the bottom there to get in touch. Thank you very much.